Okay, so I'm going to discuss with you today the three filling rules and also how to draw orbital diagrams. Okay, so first we're going to start with those three filling rules. And just let me clarify, it's not like the electrons follow these rules. It's simply that scientists have observed patterns and they have come up with these rules or conclusions, you might want to call them, that the electrons always follow. Okay, so the first one is called the off-ball principle. This principle states that the lowest energy levels fill first. In other words, like that order of filling that I gave you the other day, and of course the how you can just look at the periodic table and you know the order that they fill. They fill 1s and then 2s and then 2p and then 3s and 3p and 4s and 3d, 4p, and then we go to 5s, 4d, 5p, etc., just going left to right on the periodic table. Don't forget, after you do 6s, as in Sam, you have to go down and get 4f and then come back to 5d. Okay, so just don't forget that part. But they do fill the energy levels in order of lowest energy and increasing from there. Okay, the second filling rule is the Pauli exclusion principle. This one states that in order for electrons to occupy the same orbital, they must have opposite spins. In other words, counterclockwise and clockwise spins. Think of a top. The example that I used in class the other day was when I was little, I had this top that I used to play with and I would spin it. And I, loved to watch the design on the top of the top, the upper surface of the top, and the pattern that it would make as it would spin. And I was always intrigued because when my dad would spin it, it looked very different than when I would spin it. And then I finally realized that it was because my dad was left-handed. So where I would spin it and the top would spin clockwise, when my dad would spin it, it would spin counterclockwise. And it looked so different. The reason for this is an electron is a charged particle. And when a charged particle spins, it creates a magnetic field. And this magnetic field, just like having two of the south poles of a magnet or two north poles of a magnet together, they push each other away. That would be the same situation if we had those electrons spinning in the same direction and they were occupying the same orbital. They would push each other out. And so to avoid that, electrons have to have opposite spins in order to share space. The next page, or the next thing that we're going to talk about, Okay, the next filling rule that we're going to talk about is Hund's rule. Okay, so Hund's rule is the third filling rule, and this simply states that electrons do not share an orbital until all of the orbitals in that sublevel have one electron. The example that I use for this is the bus example. If you will imagine, please, a bus that has 25 seats, and you have 25 introverts getting on that bus. Imagine, if you will, what the 25 introverts do when they get on. They likely sit in their own seat by themselves. They don't share a seat. They wouldn't share a seat until that 26th person came on the bus and they realized that they had no choice but to share a seat. That's the exact same thing that the electrons do. Okay, now we will begin discussing how to draw orbital diagrams. First, we start by writing the electron configuration. For example, nitrogen looks like this. 1s2. Actually, let me add the... Okay, so we put the chemical symbol at the front, and then it goes 1s2, 2s2, 2p3. Again, we can verify that we have the right electron configuration simply by adding up the superscripts, which the superscripts represent the electrons, of course. And when we add up those superscripts, we obtain the answer of 7. There are 7 protons in nitrogen, and when it's an atom, there are also 7 electrons. The big numbers in this electron configuration, such as this 1, that 2, and that 2, represent the energy levels, also called the quantum number. The letters here, such as the S and the S there and the P there, represent the sublevels within that main energy level. The superscripts, such as the 2 and the 2 and the 3, represent the electrons. Then, when we're drawing the orbital diagrams, we use that electron configuration to draw the boxes. One box by itself represents the S sublevel. 3 boxes attached represent the P sublevel. 5 boxes attached represent the D sublevel. And 7 boxes all attached represent the F sublevel. When I draw these, how I do it is I draw a rectangle and then I separate it into its smaller components like that, rather than try to draw the boxes individually. It doesn't really matter which way you do it, though, of course. For example, the orbital diagram for nitrogen looks like this. As I said, we begin by writing the electron configuration, which is 1s2, 2s2, and 2p3. Then we draw our boxes. An S, remember, is represented by a single box. We draw the single box, and then we place the electrons in the box. We have 1 up and 1 down because we have 2 electrons in that sublevel, just like is shown here in the electron configuration. Then we have a 2s orbital. We draw a single box. We have 2 electrons in there, 1 up and 1 down. Then we have a p sublevel, 2p3. So then we draw our 3 boxes all connected, and since there are 3 electrons, we put 1 electron in each of the boxes. We always start with our up arrow first. Notice I did not put 2 arrows in one box because there are only 3 orbitals in a p sublevel. Therefore, each of those 3 electrons get their own orbital until that 4th electron would come into play. In orbital diagrams, the boxes represent the orbitals and the arrows represent the electrons. The direction of the arrows, whether they go up or down, represent the spin of the electron. Okay, so now let's try one more example together. Let's do chromium. Okay, chromium is in the D block. So we start by writing the electron configuration for chromium. One S2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. We can double check ourselves and make sure that we have the right electron configuration by double checking that this is in fact the order, and also counting up the electrons, which are represented by the superscripts, and making sure we have the right element. 2 and 2 is 4, and 6 is 10, and 2 is 12, and 6 more is 18, and 2 is 20, and 4 is 24. The atomic number for chromium is 24. This means that chromium has 24 protons, and since it's an atom, it has 24 electrons as well. To represent the 1s sublevel, we draw a single box. Since there are 2 electrons in there, we have an arrow going up and an arrow going down. We draw the next S sublevel, and again, there are 2 electrons in there, so we have 1 going up and 1 going down. Then we have a 2p orbital, and there are 6 electrons in here, so we have 1 arrow going up and 1 arrow going down until we get to 6 electrons. Then we have a 3s with 2 electrons in there, and again, we have an arrow going up and an arrow going down. For the 3p6, again, we have an arrow going up and an arrow going down. And the last 2 look like this, 4s2 with an arrow going up and an arrow going down. Whoops, I forgot that's a D, not a P. So here we have 3d4. So I have an up arrow in 4 of these orbitals and nothing in the last orbital. Okay, so there's nothing in the last box. I'm going to try to draw that a little bit straighter. Okay, so we still draw that fifth orbital, although it has nothing in there. So we still draw this. Even though it's empty. Okay, so I believe that is all I need to really show you on orbital diagrams. If you have any questions, I highly suggest you watch this again. Make sure you have your periodic table next to you because that will help you greatly. And as always, if you have any questions, just reach out. Thank you very much. Have a great day.